Now we look at the code that actually generates this neural network that we have over here into a Bayesian framework. So what the code is going to do is we're going to have two for each observation. We have an x1 and an x2. So these are the coordinates in the two-dimensional plane of the picture that we saw before. That's going to be mapped into the first hidden layer, which has 5 nodes. Then there is a second hidden layer which also has 5 nodes. And the second hidden layer is mapped into a probability. So in a one-dimensional thing, and that's the probability that y will be equal to 1. Yeah, so this probability determines whether the y value is 0 or 1. Or in terms of the graph that we looked at before, whether the dot is going to be blue or red. So I'll just walk you through the code. So this is the part that we know. So with model as a neural network, but this thing is now wrapped into a function. And that function takes 2 arguments, the inputs, so that's the x matrix, and the output, which is the y matrix of 0s and 1, whether the dots are blue or red. Here we specify that the number of nodes in the hidden network is 5. And here we use something that actually we didn't use before, I think. We specify the initial values for the weights. So we're going to have prior variables in a second. And these prior variables are going to be drawn, of course, from the posterior distribution. So later on we're going to draw from the posterior distribution to generate the posterior of these prior variables. But here we're going to give initial values. So where the posterior sampling should start. And these are given by init1, init2 and init-out. So you're going to see in a second where we're going to need this. So we're going to need them here. So let me talk you through it. So what's happening here, this is the set of weights that maps the first layer into the first hidden layer. So this is, so we just draw random numbers here. So the initial values are randomly drawn. We start with x shape 1, so that is the second coordinate of the shape of x, which in our case is 2. Yeah, because we have x1 and x2, so we have 2 coordinates. So that 2 is going to be mapped into 5 nodes for the hidden layers. Yeah, so in terms of the simple graph that we have here, this is basically, these are the coefficients on the link between x1 and this first node, x1 and this second node, third and fifth node, and then the same for x2, the link between x2, the first node, x2, the second node, etc. Yeah, so basically that's going to be a matrix of the dimensions 2 by 5. The relevant coefficients on the second hidden layer, so that's basically the mapping between all these circles and the circles next. So that is going to be 5 by 5. And finally the weights on the final layer, so that's from the second hidden layer to this probability. So there are going to be 5 of these links, 5 of the coefficients to map these activations into the probability. Yeah, so that's exactly what you see here. So how does this end up in our model? So here we have our first prior. So we have the name of this matrix in this case. It's called weights 1. So again, we repeat the name weights 1. So the prior is going to be drawn from a normal distribution with mean 0, standard deviation 1. And the shape of weights is going to be 2 by 5. And here you see this testval keyword, which is basically something like an initial value, an initial guess. Yeah, so that's this init1. These are the things that we just discussed over here. So then the weights from the first to the second layer, so from the between the 2 hidden layers. So again, we specify weights, we repeat the name over here. It's normally distributed, mean 0, standard deviation 1, and it's of the shape 5 by 5. And again, we give some test value here that we defined here above. Then finally, we go from the second hidden layer to our output layer. So we have the name of our vector in this case. It's not a matrix, it's a vector. We repeat the name of that vector. The prior is going to be normally distributed, mean 0, standard deviation 1. And the shape is just going to be the number of hidden nodes, and then it maps onto the probability. So it maps onto a one-dimensional thing. So the comma here means that this thing here is a tuple. And again, we specify some test value. So now we get the neural network, so we get the activations. So the activations of the first layer is the matrix multiplication of our input, so that's our x basically, and we multiply it by the coefficients that we have for this mapping from the inputs to the first hidden layer. Yeah, and as we saw above, these weights are of the format 2 by 5. Yeah, so indeed I can multiply my X matrix by these weights. Then the second activation, so this is between the two hidden layers. Again, I have this multiplication of the first activations that we had over here and the coefficients to the second hidden layer. And then finally, the output of our network is going to be this multiplication between the activations that we had before, and we multiply this by the coefficients of the final layer, and that's mapping into a probability. Yeah, so that's what these products are doing here. Now we have different activation functions. So in the first two layers we use the hyperbolic tangent, so we have that here and here. And in the final layer, of course, I need my probabilities to be between 0 and 1, so we use the sigmoid for that, because it will guarantee that I have these probabilities between 0 and 1. Yeah, so basically this whole thing is the model that we're interested in. Now, as a convenience, we have this code over here, which is a bit hard to read, but the trick is here that we get this variable p that we're defining here, and that may be useful later on when we look at our trace, that we can directly refer to p and we do not have to recalculate it ourselves from the different weights that are estimated in the model. Yeah, so this deterministic we've seen before, so it is a way in pymc3 to define an additional variable which is no longer stochastic, so no stochastics are added. But of course p is random because the outcomes of the activations above are actually random. Yeah, but I define a new variable here in terms of pymc3 variables that were defined before. Yeah, so you see again these pymc3 variables that we defined above are weights in 1, the weights 1, 2, and the weights out. Now basically this is a complicated way to write exactly the same as what we've seen over here. Yeah, so if you get confused by all the parentheses, that's understandable. I'll try to talk you through it, but if you don't get it the first time, don't worry about it. So here basically what we do is we get, these are the matching parentheses. So the sigmoid, so this is actually the output layer. So we're working from the outside to the inside. It's the product of, so again we can use this thing here. So it's a product of the activation that's defined here with the weights that we have on the final, the coefficients on the final level when we move from the second layer of hidden nodes to the output, which is a probability. Yeah, so that's the multiplication that we have over here. And then what is this multiplication? This multiplication is the activation from the level above. And the activation, so I'll call this here the activation of the second layer. So that activation is based on a multiplication of the activation of the first layer and weights 1, 2. Yeah, and the activation of the first layer is given by this expression over here. So there's a hyperbolic tangent of the multiplication of, and here we don't use input as we did over here. So here we used x. But when we calculate this variable p, we're actually going to calculate it for every value on the grid. Yeah, so we define this grid variable, which is basically gives us all the points with a certain density in the two-dimensional graph that we saw before. And we're going to generate this probability for each of these points. So we're going to multiply this grid with the weights that we have in the first layer. Yeah, so that's the first activation. Then the second activation is the multiplication of this activation with the weights that we have when we go from the first to the second layer. Yeah, so that's this multiplication. And then finally the sigmoid is the multiplication of the last activation and our weights from the second hidden layer to our probabilities. Then to close our model, we specify our outcome, so what we've before called observed. So we repeat this word outcome. Because it's a 0, 1 label that we need to predict, so blue or red. This is a Bernoulli process, so it's just a throw with a coin, and it's either a throw with one coin, basically, and it's either head or tails, so that's a Bernoulli process. So here it's not head or tails, but it's blue or red. So we have a probability for that, and the probability is actually given by the activation of the final output of the neural network. So that's what this probability is. And we have such a probability for each observation. Observed is the output, so that's the y variable, which is either in 0 or a 1. And then here we can specify the total size, which is important for mini batches, but actually we're not going to use mini batches, so you don't need to worry about it. So in that sense, it's actually in our case not necessary to specify the total size. And this function that were defined here, so the function that started here, above, here's where the function starts. So this construct and end function, what it returns is actually this neural network that we defined here with pymc3. Yeah, so the function returns the neural network. And then we can call this function. So basically what we say is we define the input and the output. Theano is the backend of pymc3. So we define here a shared variable for the input and the output. So it's shared with Theano. Then we call this function that constructs the neural network with x-train and y-train. So I can run this code. Let's see whether there are no mistakes here. No, that seems to be working fine. And since this can take quite a while to sample from if you use MCMC, so Markov chain Monte Carlo, again we're using ATVI here, so it's a bit so it goes a bit more quickly. So we can run this code cell, and then we can generate a trace by drawing 5,000 elements from the posterior distribution. Yeah, so we're not going to wait for this to finish in this video, but I'll continue later on after this process has finished. So this is the optimization step to approximate our posterior as well as possible using well-known analytical distributions, and then we generate a trace. And in the next video we're going to analyze the outcomes of the model and the trace.